Hello everyone, thanks for coming for our next meeting, fourth episode of Warsaw Quantum Computing Group. Today's lecture will be given to you by Dawid Kopczyk, and he will tell you about Grover search algorithm, explanation, and classical simulation with pyQuil. So as some of you remember from our previous meeting, or maybe from our YouTube video, last time we met also here in January, and there was introduction to programming quantum computers with using pyQuil. It was given by Michał Stęchły. So today is just a continuation, and Dawid also will show some examples of code in pyQuil. The video from the previous meeting is already available on YouTube. Today we also have recording, so the video will be also available in probably a few weeks from now. And yeah, the previous meeting was supported by Daft Code. We are very happy that they support us, and yeah, today they are also our sponsor, strategic sponsor. Yeah, so at the end, as usually, I will tell you some information about our plans for the future. Before that, and before I give a voice to Dawid, I would like to mention also about one more interesting thing. So beside our video recording from the last meeting, there are also some videos about quantum mechanics, introduction to quantum mechanics for data scientists, people with expertise in machine learning, prepared by Center of Theoretical Physics from the Polish Academy of Sciences. These videos are also available on YouTube, and we already published links to some first videos. The next videos will be available soon. So yeah, I hope that you will enjoy those lectures as well. So now, Dawid, the floor is yours. Thanks once again.
Thank you, Paweł. Once again, can you hear me well? Good. So let's begin. So the Grover search algorithm is the topic of today's meeting, and the talk will be divided into two parts. The first part will be about the explanation about the basics and theory of Grover search algorithm, and the second part will be the implementation of pyQuil. So you may ask why exactly this algorithm, and the reason for that is it's quite basic and simple algorithm, and it serves us as great introduction to start the journey of quantum algorithms. So as I previously mentioned, firstly I will go through some introduction stuff, and then we'll describe the algorithm in a step-by-step manner with some theoretical facts and with some basic components of this algorithm. And then we'll implement this algorithm in pyQuil. This is a regedit package for high-level quantum programming, which I found very intuitive, and it's just a great place to start your quantum programming. So the main aim here is that, as I previously mentioned, the Grover search algorithm is a great place to start if you want to learn quantum programming. And on the third meeting, we already have introduction to pyQuil programming. On the first meeting of Warsaw Quantum Computing Group, we have basics about the quantum computations, and this will be a great, let's say, basis for today's talk and for our first quantum algorithm. The objective here is you will learn the basics about the algorithm, but I will not explain you why it works, so I don't go deep into the interpretation of quantum mechanics, but I will explain you rather how it works. And I think it's just a great way of thinking about quantum computing for the people from computer science. And I also like to explain stuff by implementing that. I found it very convenient and effective to learn about quantum computation if you do some coding. By the way, how many of you are from computer science background? Okay, so quite large part. The assumptions about this talk is that you already know something about quantum computing, like what are the gates, you know what is wave function, and you know what is qubit, and you are familiar with the Dirac notation, which is just a bracket notation. You've been, or you know, some high-level quantum programming language like pyQuil, and you know a little bit of Python, but about these two last points, don't worry. I think it will be pretty straightforward and intuitive, so even if you don't know how to code in Python, I think it will be pretty straightforward. So just a small introduction why I'm here. So I'm coming from the actuarial science background, so this is mathematics and statistics in insurance companies. I've been doing that for over 6 years, and I'm qualified actuary in Poland and United Kingdom. I'm also currently the founder of and chief data scientist of Quanti. That is a company that specializes in data science and advanced solutions for insurance companies. And after my working hours, I was always trying to learn by myself the quantum mechanics and quantum field theory. And like 3 or 2 years ago, I was interested in quantum computing. And now it's actually the great time that I live, that something that I do in my work, which is machine learning, can be connected with my passion, which is quantum mechanics, in a form of quantum machine learning. And I found it just interesting and amazing. So as a consequence, I have a blog about quantum computing, and I also cooperate with Bohr Technology. This is a Polish startup that does some quantum algorithm for business. Okay, so let's go to the algorithm. And I just wanted to point that the algorithm was invented pretty old time ago. It was 1996. So it was before the time that even somebody imagined that in 20 years we'll have quantum computers. The Groover search algorithm, and the advantage of Groover search algorithm is that it solves the unstructured database problem, and it speeds up the solving of this problem quadratically, which is quite significant speed up for large problems. You might see that the title of the paper is Fast Quantum Mechanical Algorithm for the Database Search, but actually it can be misleading because it's not directly intended to find an element in a database. The purpose of Groover search algorithm is rather to search through function inputs to see for each input the function returns true. So what does it mean? And this is a classical example of the unstructured database problem. So we have a list of capital N elements of binary strings of length n. And in that particular example, we have the bit string is of length 8. That gives us 2 to the power of 8 combinations, which is 256. And the unstructured database problem relies on having some function that is able to recognize for each input the function returns true. And there is exactly one input that meets this requirement. And this is basically unstructured database problem. So whatever problem you have that is possible to be transformed into that kind of statement, then you can solve this problem with the Groover search algorithm, at least theoretically. And if you look back on this list of 256 elements, in the worst case, the classical algorithm takes capital N queries to solve this, to check whether the input returns true or not for the function. But in average, it takes capital N divided by 2 queries. However, in summary, this is still the linear in capital N. What it turns out that the quantum algorithm, namely the Groover search algorithm, can do this job in around square root of capital N queries. So that is a significant speed up, not for the small n, but for the large, like 1 million or even higher. So let's say for 1 million, this is linear to this 1 million, but the quantum algorithm will solve that with around 1,000 queries. As an example of unstructured database problem, we can imagine that we have a list of passwords, and then exactly one is correct. We can encode these passwords or indices or in this unstructured array as a bit string, and then assuming we have a function that is able to recognize which password is correct or not, then we basically have unstructured database problem, and it can be solved by the Groover search algorithm. One very important thing is that Groover search algorithm is probabilistic, and it means that it gives you the correct answer with high probability. That is contrary to the classical computation, where in many algorithms we have the correct answer with 100% probability. And this is not due to the quantum noise. This is just intrinsic feature of many quantum algorithms, including Groover search algorithm. And we'll see that when we start to implement things. So how does it look like? So Groover search algorithm belongs to the class called quantum circuit algorithm, and it can be represented by this nice graph. From left to right, it's a passage of time. This starting cat is just a state of the qubit at start, and then this square with some letters inside, these are the quantum gates. And at the end, we have a meter symbol for each qubit. That means measurement. In this talk, in the first part of this talk, we'll go through each of the steps in details, but right now I will tell you the intuition beside the Groover algorithm. And the intuition here is that we start with the initialized state of all qubits set to the 0 state. Then we applied the Hadamard gate on each qubit to get the superposition of all possible inputs. And then we try to somehow increase the probability of finding the correct answer. And we do that iteratively. And when we are happy with the probability, in theory, then we can measure and get the correct answer with high probability. Okay, so let's see how to do that. We are starting with initialized state, so this is a classical state. All qubits are set to state 0. So that is pretty simple, and this is this part of quantum circuit. Then, as I previously mentioned, we put the state of a quantum computer in an equal superposition. So we apply the Hadamard gate on each qubit, and then it gives us this superposition of all possible inputs. Just a reminder, if we measure that state, then basically all of the possible inputs can be get with the equal probability, which is 1 over capital N. And in a quantum circuit, it looks like that. So on each qubit, we apply the Hadamard gate, which is represented by this square and H inside. Okay. And now we come to the Groover operator. which consists of two parts. The first part is quantum oracle, and I'll explain what is that exactly. And the second part is inversion about the mean, which will be later. The purpose of the Groover operator is to increase the probability of finding the correct answer. And how we exactly do that? So, firstly, we apply the quantum oracle. And at the beginning, when I was learning Groover search algorithm, this was the most, let's say, maybe not complicated, but got many questions to that topic. So let's focus on that quantum oracle because it's really required to understand this algorithm. So we do that by considering a simple example of 2-bit string of the bit string of length 2. And we have a function that is given to us that returns true, 1, for a bit string 1, 0, and then 0 for the other ones. So it means for other ones like 0, 0, 0, 1, and 1, 1. And the quantum oracle assumes that this is the representation of this classical function, but in a quantum world, as a quantum operator. How to do that? So the first guess, like that, this is not real true quantum operation. Why is that? Because the left-hand side can consist of n qubits, so the state x can be n qubit state, and then the right-hand side is a 1 qubit state, because fx can be 0 or 1. So this is clearly not reversible operation, and also not unitary. So that's not the way how to do that. But there exists a method of constructing the quantum oracle like that. And what it does is that for our 2 example, it just marks the correct answer by flipping the amplitude sign in front of this state. So it's called also phase inversion, as you can meet this term also in literature. And if we want to basically represent this quantum oracle as a matrix, then it looks like that, at least in computational basis. So as we see that, we can basically conclude that we already know the answer by building the quantum oracle. So why we need the Groover search algorithm at all? So it turned out that this is not true, and the assumption here is that the oracle is given us as a black box, as an input to Groover search algorithm. And this is basically the same situation like in a classical computation, that you try to minimize some function, some polynomial with nonlinear terms, and then if you analyze how fast is the optimization procedure, you don't analyze the time spent on building such a function. So it's exactly the same case in here. So we have a quantum oracle given as a black box, and Groover search algorithm, it just accepts this as an input. So as I already told you, this matrix representation already invites the answer, but there is a certain distinction between recognizing the correct answer from knowing the correct answer. So we can basically recognize the answer without knowing the answer. A great example is factoring problem. So we have a large number, and we try to search the prime numbers that are multipliers of this large number, and it's quite easy to check if some p and q, which are prime numbers, are the correct solution to the factoring problem by multiplying and checking the results. But it's extremely difficult to find the p and q, which are the prime numbers, which are solutions to the factoring problem. And in the classical computation, using some reversible computation, it's quite easy to construct the classical circuit that will check whether these prime numbers are the correct answer or not. And this is basically the same in quantum algorithms. So that's somehow the assumption that we have, that the quantum oracle is given to us and is able to recognize the solution to the problem. And if you want to represent that on a quantum circuit, then basically it looks like that. So we apply the OR gate, which is quantum oracle, to all qubits. So what the quantum oracle does in general is that, as I previously mentioned, it marks the correct answer with flipping the amplitude side in front of it. But what does it mean for us? If we measure this state, we still have 1 over capital N probability to get each of this state as an effect of measurement. So we need to somehow increase the probability of finding the correct answer. And the answer to that is inversion about the mean. And to explain this, I will start with some classical vector of integers, 1, 1, minus 1, 1, 1. The mean of this sequence of numbers is 0.6. And the inversion about the mean is just a reflection about this line with the mean. So it looks like that. So 1 becomes 0.2, and minus 1 becomes 2.2. And as you compare it to the previous state, then you will see that the ones becomes smaller, and then the minus 1 becomes quite high. We can apply the same logic to our quantum algorithm, and to see that, we start with our n equals 2 example that picks out the string 1, 0. We start with the state in equal superposition, which looks like that. And then the first operation is quantum oracle. It flips the amplitude sign of the correct answer. In that particular example, the mean is 0.25. And then we do inversion about the mean, so about this red line. And as a solution, we have the probability of 1 in front of the correct answer, and then rest of the answers, the probability for them were shrunk to 0. But this is, well, I told you that Groover search algorithm is probabilistic, but for this special n equals 2 example, it actually gives us the correct answer with 100% probability. The question is whether we can represent this inversion about the mean as a quantum operation, so as actually the unitary matrix. And it turned out that yes, and this is the form of this quantum gate. So we have on diagonal, we have minus 1 plus 2 divided by 2 to the power of n, and then on the off-diagonal terms, the off-diagonal terms are 2 divided by 2 to the power of n. Just to check out, for our simple example, n equals 2, the operator representing inversion about the mean is given on the left-hand side, and then it's just exactly the same representation as I showed you before. So it gives you the correct answer with the probability 100%. On a quantum circuit, it turns out that there's two parts of quantum oracle, and then the inversion about the mean, which is denoted by capital D, can be just merged into one operation, which is Groover operator. And as I previously mentioned, the aim of this Groover operator is to increase the probability of the correct answer. But what about other examples? So the n equals 2 was special case. Let's analyze n equals 3 that picks out string 1, 0, 0. So we start that kind of chart, and the probability of amplitude in equal superposition is 1 over square root of 8. This is around 0.354. We apply the oracle, so we flip the amplitude sign in front of the correct answer. Then we apply the inversion about the mean, and clearly it increased the probability amplitude, but the question is, can we do more? And if we apply the Groover operator second time, indeed it increased the probability amplitude, which means that it also increased the probability. So now to find the correct answer, if we measure 3 qubits at the end of this algorithm, is 0.972 to the power of 2, which is quite high, but it's not 100%. That's why I told you that the quantum algorithms in general are probabilistic in the nature. So this how it looks, the algorithm now. You might ask how many iterations we need to do of Groover search algorithm so that we don't overcook the solution, and it will be enough to find this correct answer. And the answer is simple. It's integer value of p divided by 4 times square root of n. How we get this number? There is a nice explanation. If we analyze 2 perpendicular states, one is the solution to the problem, and it's given by w inside cat, and then the second is the sum over all states, excluding the solution, which is denoted by S prime. Then these 2 states span the 2-dimensional plane in the state space, so in multi-dimensional space. Now, after applying the Hadamard gates, we start with with the state C1, which right now is denoted as S. And if you look on the geometrical representation of Groover search algorithm, it looks like that. So the S state is closer to S prime, and then we might ask what actually the quantum oracle and inversion about the mean does with the state. So first, the quantum oracle is a reflection of S about the S prime, and we land below the S prime. Next, the inversion about the mean is just the reflection about the S state, and to reflection gives us rotation, and this rotation is characterized by the angle theta. And it turns out that if we do enough iterations like that, then we'll be closer and closer to the winner, so to the W state. And it can be computed how many iterations like that we need, because the theta is just 2 times arc sinus, of 1 over square root of n, and then the probability of finding the correct answer is given below, and this probability is maximized. If we maximize that, we get around square root of n, or to be precise, the p divided by 4 square root of n. Groover operator iterations. So this is why we need to implement this Groover operator this number of times. So we end up actually with the Groover search algorithm in a final form. So just to sum up, we initialize the quantum computer, and we initialize the qubits in all of them in 0 state. And then we apply the Hadamard gates just to have this equal superposition state of all possible inputs, and then we try to increase the probability of finding the correct answer when we measure by the Groover operators. And as I previously mentioned, the classical algorithm is linear in capital N. The Groover search algorithm is relies on around square root of n queries. But you might ask, well, if the classical query is executed in 1 second, but the Groover search algorithm, the Groover operator is executed in 5 seconds, then of course, or even 10 seconds or 100 seconds, then you might ask that there is no speed up, but there actually is. And for large capital N, even if the application of the quantum gate is quite long compared to the classical query, then we still have, after some capital N, the quadratic speedup. This is not yet a holy grail of quantum algorithm, which is exponential speedup, but well, for many problems with quite large lists, this is quite significant.
So what's the problem in practice? Yeah. Why isn't aren't there like already have an application of quantum computing in practice? Because it definitely looks like some probably could apply.
Okay.
It's like the amount of in this amount of gates, the quantum state will for now collapse somehow.
Okay, so if I understand you correctly, you ask why we don't have the Groover search implementation right now.
Yeah.
So there are some limitations of the Groover search algorithm, and I will speak about them just in 5 minutes. Okay? But this is kind of this is a good question, but the world is not so pink right now. I have 3 side notes which are quite important to the Groover search algorithm, and the first one that you can meet in literature, the alternative definition of quantum oracle, and we define it as above equation, but actually in literature you can find that kind of equation with the O plus sign, which is exclusive OR. But it turned out that these definitions are equivalent to each other. I can show you that. So if we have this definition of quantum oracle, then why in some literature we can meet that kind of definition is because it's from the computing side, it's quite natural that the classical circuits can be represented by quantum oracle by doing that. So it's, if you have a classical circuit that serves as a classical oracle, then it's straightforward to invent the quantum oracle that does the same job. And there is just one additional qubit, which we call also control qubit, and it turned out that if this qubit is in a superposition, this superposition can be easily get if we have qubit in state 1 and then we applied Hadamard gate, then we get this state. By the way, can you see people from? No, you can. Okay, I will try to write the larger cat. So what is this operation is exclusive OR operation, and I will give you the quick review on that. If we have Q in 0, then basically the exclusive OR operation does nothing to fx. So it will look like that. But if the control qubit is in a state 1, then it will flip the state. So 1 becomes 0 and 0 becomes 1. So this is exclusive OR operation. I guess somebody of you might already know that. So now we have the Q state in a superposition. Well, actually, it should be like that. So now there are two cases. If fx is the solution, if x is the solution to the problem, then fx is 1, and if it's not, then it's 0. So we'll have in one case this thing. And in a second case, this is if x is the solution to the problem, if x is not the solution to the problem. And if we do this exclusive OR operation, then we might end up with this thing. Which is exactly the same as the above equation. We'll turn on in a minute. Okay, so that was one side note. And then I know I told you already why. I told you already that I'm not explaining why the Grover search algorithm works, but this is one exception. Basically, the main reason why this quantum algorithm is theoretically faster than the classical one at least it requires less queries, is that it uses the properties that are only interesting for the quantum algorithms, and one of them is quantum parallelism. In short words, it just quantum parallelism relies that we evaluate some function fx for all values of x simultaneously. How we can do that is that we have the state, the first registry, the x state in a superposition of all possible states, and if the control qubit is 0, then it turns out that we end up with the superposition of all x's in the first registry and then the evaluated functions in the second registry. And this is almost as if we evaluated this fx for all values of input simultaneously. I'm saying almost because when we try to measure that state, then it will collapse to one of the possible inputs. So there is no real value. This is why we need to use some tricks like the inversion above the mean in Groover's search algorithm to have some value from the quantum parallelism. And then the third, last side note is that, as I previously showed you, the inversion above the mean is quite big matrix with the of diagonal terms and diagonal terms, and it's quite difficult to implement, the matrix that we have as an operator. So in reality, we decompose this operator into set of the smaller quantum gates. And for the inversion above the mean, it's possible, and it looks like that. So this is just to show you that basically, if you have large quantum operator, then on a real quantum device, it should be decomposed into a set of smaller quantum gates.
Sorry, how much entanglement is this gate in the middle?
Hmm?
What is this gate in the middle exactly?
Okay. So this is a multiplicative C0 gate, which can be also decomposed into a set of the smaller gates. But yeah, this is
So
basically.
You control like all those n-1 qubits control the last one.
Yeah.
Okay.
Basically,
So
yes.
Highly entangling.
Yeah. So basically, the first n-1 qubits are control qubits, and then the last one is the thing that is changed. But there are some limitations of these quantum Groover algorithms, of this Groover algorithm, and the main limitation is that if you have quantum noise, which is a reality of today's quantum computer, then the successful rate is quite small. So it turned out that even if you have small quantum noise, then for the 3, 4, 5 qubits, then already the success rate of finding the correct answer is blurred. And I will show you that when we start to implement the Groover search algorithm in pyQuil. The second limitation is that it's quite sensitive to the number of iteration. So if you apply too many iterations, then it will overcook the solution, and it will be actually more far away from the correct answer. So we have to be very precise in the number of iterations. And I already mentioned that Oracle should be treated as a black box, but if you have a problem in the classical problem, the database search problem, in which the Oracle implementation is much longer than the search problem itself, then you can also expect that the quantum Oracle implementation will be overwhelming the advantages of that we get on the search problem side. So, yeah, implementation of quantum Oracle is quite difficult. But as I previously said, we always look on the Groover search algorithm separately, And if I'm saying that it requires square root of n queries, this is what I mean without implementation of quantum oracle. So if you have any questions, then you can ask them now. After the questions, we'll have a short break, and then we will start to implement this algorithm in the pyQuil.
Can I ask, the Google has a quantum computer with 72 logic qubits with quantum cubic gates, and how big search you can do on this computer? So you mentioned that Grover algorithm can be used to find passwords. It's the same like symmetric cryptography to find the key in block cipher, and it's so 72 qubit gates. It means that you can search over the space to do the 72, or
yeah. If you so basically, if you have 70 qubits, and assuming that these qubits are fully connected in a quantum computer topology, and then they are basically perfectly fault tolerant, then indeed you can search through 2 to the power of 72 space. So it's quite big space. But the thing is that
in cryptography we need something to the power 128. Okay.
Yeah. Yeah, the thing is that the Google quantum computer, it's not fully connected, so some qubits cannot interact with each other, and of course there is still quantum noise. I will show you that basically if you have quantum noise that today's quantum computer has, then even on the 4 qubit case, there's so much quantum noise that you cannot discover the correct solution. But if we have fully error tolerant quantum computers, and then they will be fully connected to each other, then 128 qubits will serve to crack the 128-bit password.
100. So one remark more. In cryptography, there are so-called hash functions, and for them there is the collision problem to find 2 inputs with the same output. It is a birthday paradox. And I read only that using quantum, and in classically, the searching for these collisions, it has a complexity to the square root of 2 to the n, so 2 to the n over 2. But I read, but I don't understand this, by using Grover algorithms, the complexity would be 2 to the power n over 3, so cube root from the size of the inputs. Have you?
Yeah. So firstly, in that example that you mentioned, the d is the small n. So 2 to the power of d is 2 to the power of n. So the Grover search algorithm is because 2 to the power of n or d is equals to capital N. So we still have the same. But if you have the extension of the algorithm that you don't search for one particular input that returns true, but let's say more, like 2 or 3, then this the square root of n changes into some other numbers. But I also read about the fact that Grover algorithm is used, can be used in collision problem. Yeah, exactly, as you mentioned. So it relies basically on the same logic here. And I will talk about extension of the Grover search algorithm after we do the coding.
And you mentioned also about factorization, and factorization, we have a Shor algorithm, quantum
Exactly.
Shor algorithm.
Yeah, so of course. It was just a classical example to explain you the inner workings of quantum oracle, and we take the factoring problem, but of course Groover search algorithm can also solve the factoring problem, but there exist more efficient algorithms to do that, like Shor algorithm problem, which do that not in the quadratic, not in a quadratic speedup, but in an exponential speedup.
Okay. So I have a question to this oracle. For an oracle, we choose this function which flips the correct the solution. So why we cannot choose an oracle which just sets the correct solution to 1 and others to 0 or something like that? I don't understand. I don't understand it.
Yeah, okay. I understand that question. Actually, good question. So we actually does this oracle because this is just you can merge two quantum gates into one, and if you merge quantum oracle with the with the inversion about the mean, then you get an operator that increases this probability. But when you were trying to explain the quantum algorithm, then there are certain steps which are clear to explain. So you don't explain quantum oracle and inversion about the mean as one. It's rather good to split these two operations into two components and then explain quantum oracle first and then explain the inversion about the mean secondly. And also, so I said that the quantum oracle is given as a black box, so why we don't give the whole operation as a black box, but this of course doesn't make sense. And also it's quite difficult to do that. We have a quantum oracle that is an input, and then we analyze how fast is the search problem if we have this quantum oracle as a black box, and then we apply some other quantum gates.
I have a comment. I suspect that the question was more fundamental. So, why we cannot apply this quantum oracle to solve the problem? Yes. So if this was so classical, you have the same problem because, for example, my favorite problem is to find a telephone number if you have a telephone book. Okay. And you want to know the name if you know the telephone number, okay? So you have to have some mean of recognizing that this is the correct number, and this is your oracle, okay? So you search the second column of the telephone, and you say, oh, this is this. On the classical level, you don't see this difference between this oracle and the fact that you look at the left-hand column and you read the name, okay? But here you have this exactly. So you have to have something which recognizes the proper solution. And in this case, this was the proper solution was recognized in this way that it flipped the amplitude. Okay. So this you have to have. You have to have a mean to find the solution. And now you have to look to apply this in such a way that you really find the solution. So when you look in the telephone book, you simply scan all these numbers with your eyes, and this is your oracle. And you find the proper number, and just say, "Oh yes, this is the number." Yes. So this is why it is a black box in a sense. Okay.
Yes, that was a very good comment on that Groover search algorithm. So basically, the rest of the increasing the probability of finding the correct answer. This is the core idea of the Groover search algorithm, and if we say that everything is treated as a black box, then we don't have quantum algorithm at all. Any more questions, or yeah?
can I have just two comments actually? So just one comment is that maybe you could have mentioned that actually Groover is the optimal algorithm,
Yeah.
because one can wonder in this Oracle paradigm whether you can do better, but you can not in quantum mechanics. This is the optimal thing. The second, this like about noise. So actually, I think it was proven that you lose this quadratic speed up in the presence of noise for generic noises in the Groover search. So it's not only the case for few qubits, but more generally. That's yeah. Also, moreover, to have using current technologies, you need over the like 1,000 physical qubits to have one logical qubit that would be fault tolerant. So field is still quite far off.
Yeah, exactly. These are very good comments. So the first comment about the optimality of this Groover search algorithm, it actually shows you the some limits of quantum computations. And about the third comment, so yeah, we have quantum noise. We can do some error correction, but as you said, the number of qubits required for error correction in Groover search algorithm, when we have such quantum noises as in today's quantum computers, is so large, then we don't even have this number of qubits currently. Okay, any more questions? If not, then let's take a break and then let's code after the break.
Okay, 5 minutes?
Yeah,
minutes
seven minutes.
Okay, 7 minutes break.
Good. So start the coding part. I use the Jupyter notebooks because it's quite straightforward to present the code and then some comments. And then, as I previously mentioned, as the high-level quantum programming language, I use pyQuil, which is from Rigetti, that's quantum startup from the United States. And I found it very convenient. And for those of you that have been on the last meeting that was conducted by Michał, you already know some basics about pyQuil. And I will use these basics in implementation of Groover search algorithm. So to start, as you might remember from the previous presentation, 1 month ago, I need to start one terminal for quantum virtual machine that will run my code, and then the compilator on the second terminal, and then I can basically start. So the first part are just definitions required to execute pyQuil code, and what we usually do with Python at start. And then we'll implement the well-known n=2 example. That is, we'll assume that we search for string 10 from 4 combinations, so 00, 10, 01, and 11. And with this part, we just assign the value to the search string, and then the length of this search string is 2. I have a question from the back. Can you see the screen, or should I enlarge it?
We see the screen here.
Good. Very good. Then we need as an input, we need quantum oracle, and because we have classical simulation, we'll represent that just as a matrix. So just to underline the fact one more again, this is an input to the algorithm, and in a real quantum algorithm, if you have, I don't know, superconducting quantum computer, then you will have some scheme of laser pulses that will serve as your quantum oracle. Here in a classical simulation of the algorithm, we can already see the matrix, and we can see already for which input is the correct answer for the problem, but this is classical simulation. And we start the quantum computer. So the get_QC is just a function that we'll get as an object of a quantum computer, and we need that for that particular example. We need 2-qubit computer. So basically, it's just similar to this one. And the argument as_QVM, it means that this is not real quantum device. This is quantum virtual machine, which is a simulator to do the classical simulation of the algorithm. And then we'll write our program in a program object, which will be just a dictionary of the operations that are required. And then at the end, we'll compile this program and run it on the quantum virtual machine, or in the future on real quantum device. So exactly the same as on the presentation, we firstly start with qubits initialization. So we assume that the quantum computer is already in a ground state, meaning that all of the qubits are in a classical state 0. And then, because this is a classical simulation, we can actually view the wave function of the quantum computer at any time we want. Of course, on a quantum computer, it's not possible. So here is the state. So it's 0, 0. So 2 qubits are in a classical 0 state. And then we go straight forward to apply the Hadamard gates. And this is easily done by this kind of instruction. So in pyQuil, we just add to our program the Hadamard gate, which is applied on the qubit. And then again, we can print out the wave function of the current state. So we have an equal superposition of all possible inputs with 0.5 probability amplitude, which is 1/4 if you square it, which is the probability of finding of the particular state after you measure the quantum computer. Then we do some stuff like defining the quantum oracle and defining inversion around the mean. But what it really does is that it's just adding the definition of quantum oracle. We can pass it as a NumPy array, and then the inversion about the mean. So how does actually this I call it diffusion, but this is inversion around the mean. How does it look like in NumPy? So it looks like this. So it's exactly the same matrix as in our presentation. Then we calculate the number of iterations, and guess what? This is just one iteration for n equals 2 qubits, for n equals 2 qubit problem. And then for each iteration, we apply firstly the quantum oracle and then inversion around the mean. And this is done in this loop. We also print the wave function after each component of Grover operator. So as you can see in the first line, the quantum oracle marks the correct answer by flipping the amplitude sign. And then after application of inversion around the mean, we have the state of which represents the correct answer with probability of finding when you measure that, it's actually 100% probability that you get this state. But I underline the fact that these are just wave function printouts, and we can do that if we do the simulation Then the last step is to measure the qubits, and in pyQuil it works like that. That first you need to declare the readout output. That is classical registry that will store the result. So we have 2 qubits. If we measure that, that can be written into 2 bits. Okay, and then in this gr_proc we have defined program, and we can compile it and then run it on quantum computer, either on a quantum virtual machine, so this is a simulation of algorithm, but we can also pretty straightforward just replace the quantum computer definition with the real quantum device and run it on real quantum device. But here we do that on classical simulation. So when you run it, as expected, we've got 1-0 state. And then there's just a function to visualize outputs as a histogram. If we, let's say, execute the same procedure 100 times, so we execute Grover search algorithm 100 times, then we'll always get the correct answer, which is 1-0. But what will happen for example of n equals 3? Okay, let's go for n equals 4. So when we run it, you will see that, well, the matrix representation of quantum miracle looks like that. Then after application of Hadamard gates, we have the state of all possible inputs in superposition. Well, that's pretty messy output, but this is what this is after the 3 iteration of Groover operator. Well, so we are lucky here, but basically this is what we expected. We get the search string exactly the same as the correct answer, but if we execute the same Grover search algorithm 100 times, then we can see that on the histogram there are some cases where the Grover search algorithm returns incorrect answer. And this is just because the Grover search algorithm is probabilistic in the nature, and basically most of the quantum algorithms are probabilistic in the nature. So you'll have to repeat, like here, 100 times, couple of times your algorithm, your Grover search algorithm, to be sure about your exact answer. But the number of times shouldn't be actually significant comparing to the capital N. So let's say if we search through 2 to the power of 64 combinations of possible inputs, then I think if you repeat the Groover search algorithm 100 or 1000 times, which is significantly lower than the capital N, then you will still you are pretty sure about the correct answer. But I told you something about quantum noise and the fact that Groover search algorithm is not good in the presence of quantum noise. So let's say that right now we have a quantum computer which is noisy, and this is easily done on pyQuil by having the noisy argument to true when you use get_QC function. This noisiness of quantum computer, it's somehow similar to to what real devices has. And then we'll try to compile and execute the same program on the noisy device. So this is still classical simulation, but it somehow simulates the action of the real quantum device as we have it today. What we do is that we already have the program compiled. Let's say we'll compile it once again and then run it once again, but now QC is noisy quantum computer, and then we plot the histogram of the results. So we'll wait a little bit. Well, my classical machine is not so fast as expected. But once it's finished, you will see that, in fact, now it's quite difficult to find the correct answer. We can increase the number of iterations, the number of times we repeat the Groover search algorithm, but still it wouldn't be so satisfying. So of course, we need to firstly sort out the noisiness issue for quantum computer before we can even use the Groover search algorithm. And as you can see, well, the Groover search algorithm fails even for simple examples like n to n equals 4, which is, in fact, we can solve this problem on a piece of paper. One remark is that once we define this program, once again for 2-qubit case, then we can print out how this program looks like. And we do that by printing the program. So we can see that we have Hadamard gates applied on qubit 1 and 0. Then we apply the Groover oracle, which is defined as above. Then we apply the inversion around the mean, which is here. And then we measure both. But this is not what actually quantum computer or quantum virtual machine, which is the simulation, sees. Because we have a compiler. And this compiler actually, it converts this kind of gates into a set of gates that are right now implemented on Rigetti real quantum devices. So you can see that if you execute the compiled version of the program. So the Hadamard gates were represented by some rotation about Z and rotation about X gates. And then we can also see that the quantum oracle was decomposed into some kind of rotation gates plus control Z gate, the same for the inversion around the mean. So these are the gates that are currently can be currently executed on the real quantum device of Rigetti, which is a the quantum computer of Rigetti relies on the superconducting. So this is what actually is real executed on quantum virtual machine or quantum computer. So that's kind of important thing to note, that we need to decompose even the Hadamard gate, which seems to be a simple gate, into two gates which are understandable by quantum computer. Okay, and you can basically, if you have this code, and then instead of this, you will use the name of the real quantum computer, like Aspen 1 2-qubit B. Then it's all you need to execute this program on the real quantum device. So it's really straightforward to firstly test something on a classical virtual machine, which will serve as the medium to do the classical simulation of the algorithm, and then just one thing, and then you are ready to execute your quantum algorithm or on a quantum device. And actually, the Rigetti has quantum cloud services that are right now public, so you can enroll to this quantum cloud services, wait on the list, and then basically reserve your quantum computer in this kind of dashboard. The available right now quantum computers are till to the 16 qubits, and you can see different topologies. So there was a good question before on the first part that Google has 72 qubits computer, but it's not yet fully 72 quantum computer because they are not fully connected between each other. So you have to write your quantum algorithm in such a way that meet the requirements of the connectivity in current quantum computers. So we can see different topologies here. Our n equals 2, the small n equals 2 example, of course, can be executed on 2-qubit computer. And I meant to do that today. So I wanted to connect to the quantum computer, which is in United States, and then execute Gruber search algorithm. But unfortunately, today is maintenance work for the quantum cloud services, so I cannot do that. But once it's finished, I guess in 2 days, and then you get the access to the public services, to the quantum cloud services. Then you can use the code that I will provide to you, and then load it to the servers of quantum cloud services, and then basically change one thing and then execute that on the real quantum device, which I think is just amazing that we have this opportunity to execute something on a real quantum device. I promised you the extensions of the Gruber search algorithm, and indeed there are some. So basically what we see here is kind of what is also called amplitude amplification trick, and this kind of Gruber operator is used in other problems. One of them is what if instead of one input for which the function returns true, we have k inputs. And of course, this is a natural extension of this algorithm, and there exists a paper about that. So I will show you that on the reference slide. Then we can also solve the counting problem. So how many of these k solutions we have? And this is also a natural extension of the Gruber search algorithm. And it turned out that it's kind of natural way to transform this function into a minimization or maximization. And this is what was done in a quantum algorithm for finding the minimum in '96. So we can also do the optimization problems with the Gruber operator. And to be honest with you, if we have Oracle that serves for the minimization, then because we have Firstly, the superposition of all possible inputs. The search is done globally. So it's not like, in neural networks that the search is locally, it's done globally, which is kind of nice property. But of course, due to the limitations of Gruber's search algorithm and the fact that we have noise right now in the quantum computers, I would say more interesting quantum algorithm is QAOA, which is which recently, like 2 years ago, was invented to do some optimization tasks. So I also encourage you to search for this algorithm on Google. And then the further read, of course, the main book that I encourage everybody to read is the Quantum Computation and Quantum Information. That's like a Bible for the quantum information subject. You will find this Jupyter notebook on my GitHub. So it's quite easy because you need to search for Dawid Kopczyk on Google, and then you will see the GitHub page. And I also encourage you to read the blog about quantum computing. You can also see the post about Gruber's search algorithm. So whatever I told today, you can also read it on my blog, and also about other quantum algorithms which are more interesting even than the Gruber's search algorithm. Apart from my implementation, there is also Rigetti library for Gruber's search algorithm, which is called Groth, and also contains, for example, QAOA implementation. So it's nice to see, it's nice to read about that in, let's say, in a book, but it's also even more nice to see the implementation, at least for the people with computer science background. So yes, that's basically it. And thank you for listening to me. And I hope that your quantum algorithm journey will not finish on this talk, but will start on this talk.
Thank you. Very good talk. Do you have any questions to Dawid?
I have two questions about this transformation from matrix to quantum gate code. So my first question is, like, if I picked big N, but by big N I don't even mean that big of N, I wouldn't even be able to have this matrix in NumPy, because for example, for N20 I would have like a matrix with 1 billion entries. So is there any workaround for that currently in pyQuil? And this is my first question. And my second question is, we know that this matrix is compiled into code, and then if n is big, isn't there some problem, for example, that this code gets exponentially bigger, and we can't have it all in memory, or even like the time of executing of this quantum gate gets exponentially longer?
Yeah, it is. So actually, it's very limited. So we can do the classical simulation for, I don't know, n equals 20 or 26, maybe on some supercomputer, but that's the limitation of classical computers. And it is exactly the same case as if we want to simulate the quantum system with, let's say, 20 qubits. This is also extremely hard to do that classically. Therefore, this is another advantage of Gruber's search algorithm, that with, let's say, 1000 qubits, if we ever have a fault-tolerant, fully connected quantum computer, then we can do something which is not possible on a classical computer, because classical computer cannot handle 2 to the power of 1000 matrices.
But will the classical computer even be able to keep all the code that is necessary here? Because here, by increasing n, we get bigger matrix and then a longer representation of our like the code representing this multiplication by this matrix gets longer, and I guess exponentially longer. So doesn't that mean that for some n, we won't even be able to hold the code in our memory, the compiled code?
That is a very interesting question. So I haven't thought about that, but I assume that there are some workarounds. So for this particular Grover search algorithm, well, you can keep the Grover operator once, because then it's repeated square root of n times, so that can save memory in this particular case. For the other quantum algorithm, this is a really interesting question, and I think that there are already some ideas, but haven't thought about it yet.
More questions?
So you said a few times that it's crucial to have a fully connected quantum computer, but you can always emulate one if it's just connected, right? Because you have the swap gate, which can like bring together arbitrarily two qubits.
Yeah, so maybe I didn't mention that. So it's crucial, of course, if you execute the algorithm on a quantum device. But if you have the simulation, then this, if you use this get underscore QC function, which is here, and then you say you need 26 qubits, then this is a simulation of fully connected 26 qubits. It's not an architecture of existing quantum devices. This is fully connected. So is that what you meant? Okay, so can you repeat the question?
So you can always compile a program for a fully connected quantum computer to not fully connected quantum computer with like linear amounts of like times a linear factor of gates that you have to add.
Yeah, okay, now I understand. Yes, that's true, but then the number of gates just increases, because let's say...
But it's linear, like it's not...
Yes. Yeah. But firstly, it sometimes can be hard to do that, and secondly, well, you increase it linearly, but anyway, you increase it. So there is more quantum noise in the quantum computer. So for example, if you have the topology of quantum computer that doesn't allow you to implement the gates which are applied on the 3 qubits, then you need to decompose that into the gates that are 2 qubits or 1 qubit. And you meant that this is linear, but still the number of gates needed is just increasing. So it's better to have fully connected one.
Okay.
Well, my question is quite general. It's about Grover search algorithm and quantum error. So let's suppose that we have a way to reduce the quantum error in our quantum computer. So do you think that Grover search algorithm will work better, or there is other limitation? Why I said that, because there is some recent progress in the quantum error reduction in a recent paper from Max Planck Institute, that they made a neural network for learning of the quantum correction. So do you think that this gonna help Grover search algorithm to work better or not?
Okay, so I haven't read this paper, and I'm not sure how this quantum correction works. But in a standard case, of course, you need more qubits to implement quantum error correction, and more qubits means that you need, more qubits in a quantum computer, and then you can approach some limit that there will be just too many qubits required for quantum error correction that you have at your resources. So, but if there exists some efficient method, maybe I'm not right now a reliable person to say the statement whether this will be good or not. But for me, it will be quite difficult with my intuition, because it's even for n equals 4 example, it's quite noisy. So even if you have good quantum error correction, that it can fail for the higher number of qubits, but still 4, it's small number. If it fails for, I don't know, 100 is still, well, let's say small number. Yeah, so I'm not sure about the true answer to your question, but I'm not, well, I'm pessimist.
Okay, thank you. Any more questions? Okay. If not, then let's thank once again Dawid for a great talk. I will just give a couple of announcements before the end. Yeah, so again, I would like to recall and tell you once again about the contest that is ongoing, paneling competition organized by Xanadu. Right now there are, I think, even more than 7 people in the team. I guess that there are 7 or 8 people from our group, but recently also 2 people from Egypt joined, so we are now scheduling our next meeting, and it's possible that we'll be competing in 2 tracks, at least 2, education and software. There's also the 3rd track, which is probably the most difficult research track. So if any one of you is interested in joining, then there's still opportunity. The deadline is end of August, so we still have time. And yeah, recently there was some interesting announcements regarding Penelane library. So it's advertised as a first library for quantum machine learning. And recently Xanadu announced that they started integration of this library with PyTorch and TensorFlow, which are quite popular libraries for machine learning nowadays. So yeah, again, if any one of you is interested in joining us, then feel free to join. And our group will return in March, on 18th of March, so a bit more than 3 weeks from now. The lecture will be given by Michał Ośmaniec from Gdańsk. The title is The Race for Quantum Computational Supremacy. And just to give you information, Michał is from International Center for Theory of Quantum Technologies. So again, we'll have a guest from external institution. Yeah, let's thank once again also to our sponsor, Daftcode, for supporting us in organizing this event. I would also like to recall that we have our Facebook group, we have our YouTube account. I know that many of you already subscribe to and follow our group and our account, and also joined our mailing list. If you are new here, if you are for the first time, feel free to join. Okay, thanks once again for your attention, and thank you, Dawid, once again for a great talk. Hope to see you next time.